I think surface areas are a very interesting um, part of multivariable calculus. Um, let's derive the formula a little bit, sort of informally. Um, so pretend you got some kind of surface and in space. Take a generic point xy. So that is not the origin. So this is coming from an xy down here. And then the x direction goes this way, the y direction goes that way rather. If you take the derivative with respect to the y, then we're going to end up with a vector. If this is going up a little bit, then the vector is going to go up. And then if you take the derivative with respect to the y, again, if the surface is climbing up, then because the x is going in this direction, the vector is going to go down. And then, now these vectors are going to be already longer than unit vectors. Pretend this is a unit vector 1, 1 for now. Then because of the slope, we're going to have a longer vector when we project this one up here. Those are tangent vectors to the surface. If we take the cross product, we're going to end up with a perpendicular vector to the surface. And the magnitude of this vector will be the area of this parallelogram formed by this. Now, this parallelogram is the projection. Well, it's not a projection on the surface because it is flat, and the surface we're assuming is curvy. So this is sort of the projection, this parallelogram of this square down here. If we make this square very small, then this will be very small, and then the area of that parallelogram will approximate the area of the surface. In other words, by having more squares like that, we're going to be adding more parallelograms, which are going to be sort of parts, approximations of parts of the surface. Each one of these parallelograms will have an area that is the magnitude of this vector. So let's think about this vector. This vector comes from the cross product of this vector and that vector. This vector, if this is a vector of length 1, this vector will have coordinates 1, 0, and then the partial derivative of the function, the surface, with respect to x. This is exactly rise over run kind of thing. This is exactly the slope. This vector, on the other hand, will be 0, 1, because we go in the y direction, f sub y. And I just want to recall that if you have a slope of 3, there's different ways to look at 3. You can do 2, and well, if this is 2, then 3 would be about that. I meant a slope of, let's just say 3 over 2. You can think of the slope of 3 over 2 as 2 units to the right and then 3 units up, or you can think of it as 3 over 2 over 1. So instead of doing this bigger triangle, you can go smaller, 1.5 instead of 3, and then you end up with the same slope, with the same inclination, the same steepness. So that's what's going on here. We got a 1 and then the slope itself. That's what happens in this situation when we have a 1 in the denominator. So we're going to do the cross product of those two vectors, 1, 0, f sub x, 0, 1, f sub y. Cross them, and we get negative f sub x as first coordinate, negative f sub y, second coordinate, and 1 as the third coordinate. But we want the magnitude because the magnitude gives us the area of this parallelogram, which approximates the area of the surface. So the magnitude would be f sub x quantity squared plus f sub y quantity squared plus 1. Remember, by the way, that this is the partial, so a longer notation would be partial f with respect to x, and the notation for that is partial f with respect to y. I usually put f sub x because it's just way shorter. Okay, that would be the area of this parallelogram, which is a 1 by 1 on the floor, not 1 by 1 here because the slopes make this longer. These are the hypotenuse or triangles where 1 goes across, and then we got f of x or f sub y as the height of those other triangles. But we want to split this into even smaller pieces, much smaller pieces. Pieces, little rectangles that have a delta x, this direction length, and delta y, that direction. So that causes this to split in smaller rectangles by the same amount. Now, because we're working with the number 1, think of delta x, since it is a small number, as a percentage, like 0.1% or 0.01%, really, really tiny. So by taking a percentage of the whole, we obtain this big, this rectangle, but then we take another percentage of this whole, and that gives us another, I meant to go from here to here because that is 1. So a percentage of this whole gives us a distance, a long rectangle, a percentage again, because think of this as a small number, as if it was a percentage, we'll have the appropriate percentage corresponding to the small rectangle on the floor, and that would correspond to a similar rectangle up here. So f sub x squared plus f sub y squared, don't forget the 1, delta x, delta y corresponds to a small rectangle up here. We want to add a bunch of those because they approximate the little pieces of the surface of that we are trying to obtain. They approximate the area of the surface. So we have a bunch of additions here. When we take the limit, after taking the limit, then we end up with double integral. That's what double means, double addition, because we're adding rows and columns, or rows and then the little areas on each one of those rows. So this one of them adds the rows, the other one adds the little areas on each one of the rows. But it could be columns, either way. Over the region, square root of f sub x quantity squared plus f sub y quantity squared, add 1, and then with respect to the area. So that is the formula for the total surface area of a surface above a certain region R. So assume the region R is this one, down here. And then we can add all of that together to get the corresponding surface area. Let's do a practical example. Example 1, we want to find surface area of f of x, y equals x squared plus y squared. So that is a regular paraboloid over the unit circle. So pretend you got the unit circle down here, and then stretch that unit circle over the surface. We want to find this area. By the way, you can do that with calc 2, by calc 2 means, because this is the same thing as having a parabola and rotating it around the y-axis. You don't have to go back to that, but it is good to realize that this is what we are doing. So we already know how to do that by other means, by means of the calculus 2 and by rotating. So the surface area, the region, by the way, is down here. It is the unit circle, will be the double integral of derivative of this with respect to x, but then we're going to square. Derivative of that with respect to x is 2x, square that for x squared. The derivative of that with respect to y is 2y, square that for y squared, add 1 with respect to the area, which means in this case dx dy over the region. Now there's one problem. The region, that unit circle, a top view of this, of course, is going to be a circle. And so if we integrate with respect to y and then with respect to x, the integrals are going to look like this, from -1 to 1 on the axis. And then the other guy is going to look like from negative square root of 1 minus x squared, square root of 1 minus x squared positive. And then there's more stuff here. So this is just a note. This is not the actual integral. I'm just showing you what we would have. This is complicated. It is compounded with the fact that if we integrate with respect to x or with respect to y, this is already a complicated integral. I wouldn't necessarily know how to start. It's really not easy to figure out what that would be. So to avoid problems, to make things a lot simpler on us, we're going to move on to polar coordinates, because this will be a rectangle in polar coordinates. Theta would go all the way around from 0 to 2 pi. So in polar, we would end up with theta going from 0 to 2 pi and r going, and r going from 0 to 1, because r just goes from 0 to 1 in any direction, and all directions are going from 0 to 2 pi. So we got solid, nice numbers, which causes this to be a rectangle. Now, if we do that in polar coordinates, remember that x squared plus y squared is equal to r squared. So those two together make r squared, but times 4, of course. But we can factor out the 4. So in polar coordinates, we have a double integral for the theta from 0 to 2 pi, for the r's from 0 to 1, and we have square root of 4r squared plus 1. Don't forget the 1, dr d theta. I'm forgetting something. You guys know what it is. It is an extra r. Every time we convert from xy into polar, we need to include the Jacobian of the transformation, which in this case is r. For polar coordinates, it is r. That actually makes this easier, because then we can do substitution. We can set u to be, what do we want u to be? Oh, 4r squared plus 1. So du is 8r dr. So we have the r and the dr, which are the difficult things to come by. And we need an 8. So we divide by 8. 0 to pi. By the way, the r and the theta are not related. So anything related to r is a constant. So we can factor that out of the integral, which leaves us with the integral from 0 to 2 pi of 1 with respect to theta. And we still have to deal with this integral, but on the side, times this other integral, which is really the integral of the square root of u du. We already took care of the 8 out here. And u goes from, okay, so when r is 0, u is 1. And when r is 1, u is 5. The first integral is going to be 2 pi. So we still have 1/8 times 2 pi. And then this is 2/3 u square root of u. Really, it is u to the 3/2 after we do the antiderivative, but u to the 3/2 is the same thing as u root u. And then we have to evaluate this from 1 to 5. So 2 times 2 is 4, simplify with the 8. So we have pi over the 2 left over with the 3, 6, times, in parentheses, 5 root 5 minus 1 root 1, which is just 1. So this is the exact area of the surface. And we should have gotten that back in Calc 2. It is a good idea perhaps to check, although we don't want to dwell too much on the checking, although it is perhaps, again, a good idea to double check. I'm trying to see if I have that number here somewhere. Yep, it is about 5.33. Not 5.33, but about 5.33, which means now the radius, the area of the circle on the floor is just pi r squared, but the radius is 1. So this is pi. So that is 3.14. So when we stretch it up here, we end up with going from 3.14 to 5.33. So we increase the area by a lot when we stretch it over this surface. Example 2. Let's say we have a ball of radius 13, and then go from the center out 5 units. So 5 units, and then form a cylinder. So we have a cylinder caught in the ball this way. So it's a circular cylinder that crosses the ball through the center, and the radius of the cylinder is 5 units, and the radius of the ball is 13. The question is, when we do that, when we cut the sphere, we're going to have a cap here, and we want to know the area of that cap on top of the sphere. Now, the answer is not 25 pi r squared. Okay, let me do another picture. So this is what's going on. We got a cap. So this is the top of the sphere, but not the half of the sphere, just some portion of it. If you project this down to the floor, you end up with a circle of radius 5. Now that sphere keeps going down this way and that way until we reach 13. So the question is, what is this area? Now the area is bigger. The area down here is 25 pi r squared. If the radius is 5, then the area of this better be more than 25 pi. Yeah, 25 pi. I'm looking for my calculator. Anyway, 25 pi is somewhere in the neighborhood of 75. Okay. So let's figure this out. So we want to find this surface, the area of this surface. So the equation of the sphere is x squared plus y squared plus z squared equals, the radius of the big sphere is 13, so 13 squared is 169. Z will be, now since we are looking just at the top of the sphere, we can do square root of z, 169 minus x squared minus y squared. So that's the top. Yep. So this is the surface. This is F. Z sub x will be, well, you know how to find the derivative of root. It is 1 over 2 times the root, 169 minus x squared minus y squared, times the derivative of the inside with respect to x, which is negative 2x. So the two simplify. I'm thinking for the formula, the formula for the surface of the area calls for Um, yeah, the formula calls for the partial derivative squared plus the other partial derivative squared plus 1. So I want to see what happens when we do this and we square it. So the partial of the function with respect to x squared will be the 2 simplified. The negative will go away as we square. So x squared over 169 minus x squared minus y squared. Okay, this is totally symmetric with respect to x and y. So it is reasonable to expect that z sub y squared will also be y squared over 169 minus x squared minus y squared. I'm trying to put together this part of the integral. So we got this part squared, this squared. Those are those two. We're going to add them together, but then we're going to add 1 to it. And 1, since we have this denominator already, is 169 minus x squared minus y squared over 169 minus x squared minus y squared. I said that backwards. The one on top over the bottom. And then we're going to add those together. So something interesting is happening. We have the same denominator, the bottom. If we add this plus this, well, the y squareds go away, plus this causes the x squareds to go away. So the 3 together are going to give us just 169 because the other 2 went away with those negatives over the same denominator. So the surface, the surface area is going to be the double integral over the region. What region? This region of the square root 169 over 169 minus x squared minus y squared with respect to the area over the region, that region, which is a circle. Let me simplify this a little bit. Of course, square root of 169 is 13, which can factor out easily. Square root of 169 minus x squared minus y squared. Okay. So again, the region on the floor is a polar rectangle. And so we're going to change that into polar coordinates. So we're going to continue here. Let's just put a new s. In polar coordinates, we're going to have, by the way, the 13 can factor out. There's no, it doesn't matter. I guess we can leave it there. 13, 169 minus. Now, remember, in polar coordinates, x squared plus y squared is the same thing as r squared. So since we're subtracting those two, that is the same thing as subtracting r squared. dr d theta, we got a circle of radius 5. That means that r goes from 0 to 5, and theta goes from 0 to 2 pi. What am I missing? The Jacobian. R is the Jacobian. So this is an extra factor we include because when we go to polar coordinates, the areas are not as square as they would be in xy coordinates. Okay. The r's and the thetas are independent. There's no theta hanging in here, causing any problem. So we really have the integral from 0 to 2 pi d theta, which is going to give us 2 pi, and then the integral of 13r square root 169 minus r squared dr from 0 to 5. So of course, there's a couple different ways to go now that I think about it. I was going to go with trigonometric substitution, but I think u substitution will be almost faster. I don't know. So we're going to set u to be 169 minus r squared. Consequently, du is going to be negative 2r dr. So this is side notes for the reader to see. So this is 2 pi coming just from this integral. And then we got to do a substitution. Well, the r gets absorbed by the du, but we got to divide by -2. So keep the 13 out, -2 on the denominator, because we got to divide by that. And then we have the integral of, I'm going to write this. This is u, square root of u, which is u to the 1/2, u to the -1/2, because we have that in the denominator, du. Let's change the limits of integration. When r is 0, u is 169. When r is 5, we're subtracting 25, so we have the upper limit of 144. The 2 simplify, so we have -13 pi. The antiderivative of that is u to the 1/2 over 1/2, which is 2 square root of u, from 169 to 144, -13 pi. Well, I should have multiplied by 2, that's a 3, so times 2. Square root of 144 is 12, minus square root of 169 is 13. That is going to give us -1, which cancels with that -1. So we end up with 26 pi. Wow, isn't that something? Because, so the area, the cap on the sphere stretches up to 26 pi. The area, the projection of this cap on the floor, which is a circle, will be 25 pi. So it did go up by a whole pi, 3.14. I think this is very, very interesting. There's one more example I should point out. Maybe I don't think I want to necessarily finish the example. So example 3. Okay, I'm just gonna get you started, but you should finish it. So pretend you got a plane that crosses the x-axis at 2, the y-axis at 3, and the z-axis at 5. So this is a plane, not through the origin. I think we've done this before in previous videos. This plane, the equation of this plane is 15x plus 10y plus 6z equals 30. Let's double check. So when x is 2, y and z could be 0. And when y is 3, those two could be 0. When those two are 0, then y is 3. When those two are 0, then z is 5. So yep, that works. And a common problem is to find the area of this triangle. If I ask you to do that by means of integration. Don't do that by geometry. I have seen students who try to do it by finding the altitude, the height of this triangle with a perpendicular, and it works reasonably well using geometry, but that's not the point. We want to use integration. We want to practice how to find the area of this triangle using integration. So first, let's solve for z. Z is 30 minus 15x minus 10y all over 6. So that is 5, which makes sense. We start with 5 minus 5 over 2x. We have the slope is rise 5, run 2 minus 5 over 3y. When we simplify, that's what we get. So that is our function. That is f. We want to find that. So this is z. You got to find z sub x, z sub y, put it into the formula. The only thing left to do is, okay, we're integrating over what region? Let me draw the region here. So the x is 2, 1, 2. The y is 3, 1, 2, 3. So 2, 0. This is top view, and 0, 3. So we are integrating over this region, a double integral over this region. Double integral, not of this. You got to follow the formula. Remember, the formula includes, here it is, partial of, so you could have f or you can have z instead. Let me write down the formula down here. In terms of z, you could have the double integral over the region, square root z sub x squared plus z sub y squared plus 1 with respect to the area. So whether you use f or z, same as people say, same difference. So the trick is to find, this is not a rectangle, is to find the equation of this line, which I can provide. Y is equal to, it's going down, so we have a negative slope. Rise is 3, 2, x, but we start up at 3, plus 3. So this is the equation of this line. So you got to integrate over this region, you know, x goes from 0 to 2, but y goes from 0 to this line. So the surface equals 0 to 2 on the axis. 0 to negative 3 over 2, x plus 3 on the y's. But then we got the square root of z sub x squared plus z sub y squared plus 1. And z is this guy. So then there's more work to do. It's not going to be too difficult. When you finish this problem, step back, look at it, and try to see what is going on. Something kind of neat is going on with this example, and that's it. I think this is a good one to do. Yeah. All right, we'll stop here, and this is the section about areas of surfaces.